Hello, today we're going to be talking about asymptotic notation. Now, to talk about asymptotic notation, let's recall in a Cartesian graph, say we were to have a function called g of n. And let's say that as inputs go into infinity, so let's say as f of n, as the inputs here go to infinity, so this is g of n, that it's less than, or let's say in this case, greater than 0. And to say this, let's say if we have g of n right here, we have this function, and say this is 0, this is the x-axis. So as this function goes down, down, and it doesn't cross 0, we say that 0 here, 0. So 0 is the asymptotes. Asymptote. So this is 0 is the asymptote. So recall asymptotes here. And now let's say we have another function called f of n. So in asymptotic notation, we want to evaluate the running time of a function. Let's say we know the running time of g, and g is going to be our model sort of function here. G is our model function. Let's say this is g of n. And we have f of n, and f of n here, we want to evaluate its running time. And we're going to use g of n to evaluate this. Now, there are a couple different types of runtimes. Now, let's start out with big O. This will be the easiest one to understand. You mostly see this all the time. So this is the upper bounds. You probably see this a lot. The upper bound, big O of n. So let's see. So if I were going to say, I were to start this out, g of n. So we have g of n right here. And now we say big O of g of n. We're saying that this function here, that g of n is some upper bounds. Now, what if we wanted to say that g of n is an upper bound to f of n? We would write f of n is equal to big O of g of n. This equal sign here is kind of misleading, this equal sign here. Equal signs, let me write it at the bottom here. So equal means is. It's not equality, it doesn't have anything to do with equality. It just means is. So when I'm going to read this equation out right here, it means f of n is big O of g of n, which in translation means that g of n here is an upper bound to f of n. Now let me draw this out. So this means that as my inputs for f of n grows, that it will grow no larger, or it will not pass this function right here. It's upper bounded by g of n. So this is f of n. Though, let's say it can be equal at points. Let's say it can be equal, but it can't be bigger. It cannot be larger. Big O is upper bounds. We have others. We have omega, which is lower bounds. Lower bounds. We have theta, which is both upper and lower bound. It's sometimes called a tight bound, or just for simplicity, I'll usually like to call it the upper and lower bound. So it's an upper and lower bounds. So it means, so theta is basically, it's both of those. And we have little, we have little omega, not little omega, this is little o. So smaller O than big O. That's why we call it big O. So there's little o. This means strict upper bounds. So it's strict upper. Then we have little omega. This is W. So this is referring to this omega up here. That's little omega. And little omega means strict lower bound. So it's strict lower. And then we have this tilde here. And the tilde represents strict equality. Strict equality. And let's now draw f of n is omega of g of n. So omega of g of n. This means that as f of n approaches infinity, f of n approaches infinity, f of n, that it is lower bounded. It is lower bounded by this g of n. So it means that f of n will not cross this g of n. Now, if we were to have f of n is equal to theta of g of n, we have that f of n is approximately this, that it is both lower bounded and upper bounded by g of n. Now, that's sort of the graph sort of representation. And strict, the difference between strict, let's actually cover that. So say in big O, I allow, so f of n can touch. Like there's at points f of n can touch g of n in big O. Little o says that it is strictly lower than g of n. So f of n cannot touch g of n. F of n must strictly be lower than g of n. There's another terminology that is also used. So let's say that f of n, because f of n could behave in any sort of way. Let's say that f of n is doing its own thing, it's doing something weird, and it's growing, it's doing its own thing, and then it starts to act sort of similar to g of n. You start saying the point at which, let's say this up O of n, this big O becomes active, this big omega becomes active. So like f of n could be doing anything that it wants. Let's say that f of n starts out really slow, and then it starts to pick up the pace, and then starts acting as an, like g starts acting as an asymptote to f of n. This f of n right here. Now, the moment at which f of n starts acting in this behavior right here, f of n is big O of g of n, we call that the threshold. And we can notate that as 0n is equal to the threshold. So this means at input n0, we start seeing this asymptotic behavior. That's called the threshold, the thing that we could start evaluating. That's just you won't see it as much, but if you do see it and you see the n0, that notation, the n0, you'll know that that's the threshold, that this is when the function starts acting, or g of n starts acting as an asymptote to f of n. They start acting asymptotic. Now let's get a little bit more formal with our definitions. Now let's begin with f of n being upper bounded by g of n. So let's start with upper bounds. Now as we start with f of n is equal to big O of g of n. Now in this, to formally say this, we can start out with 0 is less than f of n. This is to say that, let's draw the graph right here. Our functions start out, let's say we have g of n here. Our functions start out at the origin point at 0. So it's 0 right here, the origin point. And start out at 0, they start growing and growing and growing and growing. So this is going to be f of n, and then we have g of n right here. As they're growing, they start at the origin point. So we're going to have this 0, the function is less than or equal to 0 to represent that. Now we're going to say, let's do some space, we're going to say g of n So f of n is lower than g of n, so that g of n upper bounds f of n, that g of n is greater than or equal to f of n, that f of n is, smaller than g of n, as we can see here. It's smaller than g of n, but, it can be equal, it can touch, as we've stated before, like f of n can touch the line of g of n. So we said less than or equal to. Now, there's something important to state that, like, in the real world, there could be some wiggle room here, like g of n can behave differently or in certain ways, but, like, generally g of n is running at this time, it, like, sort of generally runs this way. And, f of n, even though, like, g of n generally acts this way, f of n, is still, like, smaller than g of n. To represent this sort of, like, wiggle room, sort of uncertainty that, like, generally g of n is growing, that g of n upper bounds f of n, like there could be some wiggle room here, that, like, uses constant factor. So we're going to say C is defined as, this means defined, C is defined as a constant factor, that we say, f of n is less than or equal to g of n, like within a constant factor. There's some wiggle room, so it's g upper bounds f of n, g upper bounds f of n, but within a constant factor, within some type of wiggle room. Now, to get even more formal with this, we can talk about limits. Now, as we approach infinity, as we keep having inputs of n, as we just keep going and going into infinity, as we say limits, n goes to infinity, as our inputs go to infinity, we're examining this ratio. We're examining this ratio here. This is a ratio. This is not saying anything about the actual functions themselves. This is a ratio. This is sort of describing the overall behavior. So this ratio of f of n over g of n is less than infinity. What this is saying that, like, since g of n, since g of n is upper bounding, since it's greater than or equal to f of n, and g of n is growing larger and larger than f of n, that g of n on the denominator here is going to be dominating. And we know that if the denominator is bigger than the numerator, we're going to keep getting smaller and smaller and smaller and smaller and smaller and smaller. So this means as infinity just keeps going up and up and up, we're not going to be on par with infinity. We're not going to keep growing and growing and growing. We're going to get smaller. This fraction is going to get smaller, this ratio. So this less than infinity means that it's going to get smaller. It's going to get smaller and smaller and smaller. It's not going to keep up with infinity. And this ratio, this behavior here, describes the upper bounds. Now, to say lower bound, we just have to switch a couple of things around. So instead of less than or equal to, we're going to say less than or equal to, we're going to say f of n is greater than or equal to g of n, within a constant factor, and g of n is greater than or equal to 0. So the function starts out this way. So looking at it sort of this direction, I could write it like this: g of n within a constant factor, g of n is less than or equal to f of n. So again, that g of n is a lower bound, so this, in this case, you can kind of say that f of n is some kind of upper bound to g, but in this notation we're really trying to say that g of n is a lower bound than f of n, so that g of n, within a constant factor, g of n, our model function, is lower than g of n. So f of n is above g of n, dominates g of n, is bigger than g of n. G of n is a lower bound of f of n within a constant factor. And to say this within limits, to evaluate this in terms of limits, let's move this a little bit over here. To evaluate this in terms of limits, so this means that, let's say, since our f of n is dominating now, you know, we're going to keep going and going to infinity. It's going to keep growing. So this is to say that our function is greater than 0. Recall that in big O, that we were less than infinity because, you know, we kept getting smaller and smaller and smaller. You could argue that we're getting closer to 0. But, you know, now that f is dominating, we're going to keep growing and growing and growing. You know, we're kind of growing to infinity, f of n. So to say that, you know, we're bigger than 0, we won't ever reach 0. We're just going to keep going and going and going. That is omega. So now let's talk about theta. So we have theta right here. And theta means that it's both upper and both the lower bound. So it's both upper and lower bound. So that means if we have f of n, that g of n is both omega, not omega, this is both big O, so this is big O right here, and this is also true. So and f of n is omega of, let me write the other one here, and g of n. So it is both, g of n is both the upper bound and it is both the lower bound. This is equal to saying, this is to say that f of n is equal to theta of g of n. So it's both the upper and both the lower bounds. So let's write this, to write this out in our equations from earlier, we can say, let's leave some space, that f of n, let's start with the upper bounds, is less than or equal to g of n, you know, within a constant factor. So our constant factor here, that within a constant factor, you know, f of n is less than or equal to g of n. To incorporate the behavior of the lower bounds, we put that within a constant factor, let's say a different constant factor, c prime. That c prime, you know, within a constant factor, g is also the lower bounds. So again, g of n is also the upper bounds, and g of n is the lower bound, and f of n is sandwiched between them. So it's a tight bounds, it's sort of a loose equality. In terms of limits, as n approaches infinity, we have this sort of ratio. Let's see right here. As n approaches infinity, as we saw with our upper bounds, we had infinity as it gets smaller and smaller and smaller as g dominates. But it's also the lower bounds. So we include the behavior of our lower bounds, that for the lower bound in this case, f was dominating. It was going bigger and bigger and bigger. But in this case, it's both upper and both the lower bounds. So we're going to have this sort of lull, this sort of in-between behavior, this sort of loose equality. This describes theta, both the upper and lower bounds. Now, to talk about these strict upper bounds, that little o. So again, big O, omega, theta, little o, little omega, so little omega of this guy, little omega of this guy. This is big omega, or just omega. And then we have strict equality. This is sort of the loose, the upper and lower bound. This is a strict equality. We're going to be talking about little o, so little o. To say that f of n is little o of g of n is to say that, you write this, that f of n is strictly less than, so less than, there's no equal to, big O allowed the equal to, it allowed touching, but strict says no, like that f must be strictly lower than g of n within a constant factor, And how this plays out in our limits, that as our limit, as our n approaches infinity, as n approaches infinity, f of n, so g of n, that we get rid of all this wiggle room, that if g of n strictly dominates, that it strictly is just bigger, that this is obviously going to get smaller and smaller, that we're going to just approach 0. That it's equal to 0. That shrinks to 0. Now this is so large that it's just strictly bigger, that there's no wiggle room, that it can't touch, that it's just, as we go to infinity, it flattens out to 0. That's how we write this. Now we're going to be talking about strict lower, so little omega. So let's say f of n is little omega of g of n. Little omega of g of n. This is to say that f of n, or, well, that g of n, within a constant factor, g of n is less than, not less than or equal to, like big omega, is strictly less than f of n. That is strictly is a lower bound. F of n is not touching g of n. It is g of n within a constant factor is just smaller than f of n. To represent this in terms of limits again, we do the limits as n approaches infinity. As n approaches infinity, we look at the ratio, and this time we're going to write g of n on top. G of n on top for simplicity. G of n on top for ease of notation. And again, as we saw before, since g of n is on the top now and is smaller than f of n, so the f of n now is dominating, we're going to see the same behavior, that it is just going to equal 0. We swapped the numerator and denominator. Again, we're just evaluating ratios here. We're just using this as a tool to just, evaluate or explain the ratio to other people. I'm explaining, as a mathematician, as a computer scientist, I'm explaining this ratio. So we can be loose on notation, we can flip things around. I'm explaining to you, explaining to the world how this ratio works. So we put g of n on the top, put f of n on the bottom. And this is to say the same thing right here. Equations are loose, they're supposed to explain, not loose, but they're supposed to explain something. And we're explaining the behavior. We're trying to explain the behavior in concise notation, how f of n relates to g of n within a constant factor. So that's why we swapped it around right there. It's just to explain. This is all notation. That is little omega, which is strictly lower than. Now, here we have strict equality. We're going to talk about strict equality. And as the name may or as we've talked before, may give off, that f of n, when f of n is, usually say tilde right here, to g of n, that these are strictly equal. That we do the limits as n approaches infinity. As n approaches infinity, we are going to have f of n over g of n, that if these are, strictly equal, that means that f of n over g of n equals 1, as x over x equals 1 if these strictly are similar, have the same runtime, that the ratio of them should just be 1. This is to say they are strictly equal. That is the tilde, asymptotic equality. So now we're going to be talking about asymptotic notation in terms of n. Like, as n grows to infinity, we want to know, sort of in the worst case, how n is going to be reacting. So this requires to be familiar with sort of magnitudes of input, like how magnitudes can be represented. So let's draw this here at the bottom. So this is just going to be 1. 1 is sort of constant time, sort of math equation, something that's deterministic, something that doesn't require routines, subroutines, algorithms, which is less than log n. So we're talking in terms of n here, talking in terms of our input size is n. And then this is smaller than n, so linear time, which is smaller than n log n, which is smaller than n squared, which is smaller than 2 to the n, or some constant number to raise to the n. When n is on top, when n is the exponent, it is larger than n as a base. So when n is on top, it's larger, and which is smaller than n factorial. Now let's say we wanted to evaluate f of n. Let's say f of n was comprised of 3 main functions. This function a, and this function b, and this function c. We can say that f of n is equal to a plus b plus c. This is to say that a does its own thing, that's disjoint, b does its own thing, and c does its own thing. If these are disjoint functions, and we represent these disjoint functions with the plus, that f of n is comprised of a plus b plus c. Now let's say we were to dive deeper into a, and we said, let's say a, for here, a is some for loop. And a for loop is some iteration, some number of iterations on some item. So let's say this is an I. So for I is equal to 1, 2, this arrow means 2. So I is equal to 1 towards n. So we start at 1, or I is equal to 1 towards n. This could be represented as the summation. I is equal to n, not n. I is equal to 1 going to n. So we're just going towards n. So this is going to be the equation a is equal to n. So a is just equal to n here. So now let's say we have another disjoint for loop. This is j is equal to 1 towards n. Now this would be a is equal to n plus n. If this were a constant, this would be n plus 10. Now let's say we were to nest these. Nesting would be to put the other for loop inside the other one. So now let's start with a constant. This means that for every n, we run 10 operations. So this means we have 1 element, 2 elements, 3 elements, dot, 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 all the way up to n. So for every element, we run 10 operations. 10 operations. We represent this by saying, to use this color, a is equal to n plus, not plus, times 10. So n times 10. That's n times 10. Or we would simply write 10n, or 10 times n. Now if this were n, then it would be n times n, which is just equal to n squared. So this would be a is equal to n squared. Now I'm going to show something really tricky here, so let's pay close attention. So let's say j is equal to I. Let's draw out a table. So let's say I, j. This is, let's say n is equal to 5. This means 1, 2, 3, 4, 5. So this is the possible sort of inputs I would be. So n is equal to 5. So on the first loop, we have 1. And we're going to run j is equal to I. So this is going to run n times. Why? Because we're going to have 1. Let's say this performs some addition. So this would be like 1 plus 2 plus 3 plus 4 plus 5. So we just run this many times. This next one would be n minus 1. As we start with I is equal to 2, we get 2 plus 3 plus 4 plus 5, and so on. 2, 3, 4. So 3, start with 3, and then start with 4, and then start with 5. 4 plus 5, and then 5. This is called the arithmetic sum. Can be shown by the arithmetic sum. So this would be I is equal to 1, and so this is the same thing as our for loop up here. And then we have just I here. So this is equal to n plus 1 over 2. So if I were to if I were to do our example here, this would be a different color. This would be n is equal to 5. So let's do I is equal to 1. N is equal to 5. And this would be I. So this means 1 plus 2 plus 3 plus 4 plus 5. This equation is equal to, like the just closed form would be 5 over 5 plus 1 over 2. And that would be our equation. That's representative of n is equal to 5. Now, if we were going to simplify this, this would be n squared plus n over 2. Now, when evaluating equations, we only care really about in the worst case, like as our function is growing, what is dominating our function? What is driving our function? What is the longest this function is going to take? What's the driving force? And let's say, as an aside, we do 3n plus 3 plus 3n squared. What is the driving force? What is the largest thing in this equation? It will be this 3n squared. Because as we chase infinity, looking at this table below, we see that n squared is larger than n. And we can see that n could be equal to 1 here, so it's larger than 1, 2. That 3 to the n squared is our largest function here, or largest part of our function here. And let's say this is g of n is equal to this. Then that means that our big O is n squared. As we don't care about constant factors, we don't care about these other parts. As we grow to infinity, our big O, we're upper bounded by n squared. That's as large as we're going to possibly get with our inputs. So going back to this above, we don't care about constant factors. We only care about the largest driving force, which is n squared. So we can say that this arithmetic sum is n squared. That the big takeaway here is that even though we're doing n minus 1, n minus 2, that this function, that's sort of this occurrence, is ultimately n squared, even though this I isn't directly running n times for every n, that like in the culmination of things it still is n squared. So that's something you should always look out for. If your inner for loops or anything are just decreasing by 1, that should be a hint that it is going to be still n. So even then this is j of I, this is j equals I, you can still think of it as just 1. And that is how you evaluate functions. But let's flesh out b and c. Let's say b was just a regular for loop. I is equal to 1, goes to n, and then c is just 5. It just performs the function 5 plus 1. This means this will be equal to, so we already evaluated this. We said I, put this as I here. So this first part, so a, is going to be n squared plus n plus some constant. It could be just 6 or some math operation, but you know, this, in the grand scheme of things, is just O of 1. Just performs some constant function. So this is f of n. Now we evaluate this, and we can say that this function is O of n squared. It's our dominating term here. Dominates the function, so it's upper bounded by n squared. So now let's work out an example. Let's say we had f of n is equal to 3n squared. Let me do this better. 3n squared plus 2n plus 1. And we had g of n, which was just n squared. If we were to boil this equation down, you see our dominating term here, so that would be n squared. So our dominating term is n squared. N doesn't grow large enough. We don't really care about constant factors. Just big O is within a constant factor. So we can boil this down to big O. And we see g here that, you know, n squared is really just, you know, n squared. There's no other term in the equation. So how does f of n relate to g of n? Well, n squared and n squared, well, n can't really grow any bigger than n squared, so we could say that f of n is big O of g of n. And, well, n squared doesn't really get any smaller than n squared, so we can say that f of n is equal to omega of g of n. And then we can say that since they're both upper and lower bound, that we have f of n is theta of g of n. And that is the conclusion of the video. There is a more concise version of the video in PDF form in the description below. It is open source, has code examples, test examples, more examples, working through even the strict upper, lower, and equality examples. Yeah, just test questions. If you want to contribute, it is open source. You can contribute, fix a typo, add any content that you, the viewer, feel that is helpful. And if you enjoyed this video, don't forget to like and subscribe. Thank you.